Hi everyone, this is Dr. Hopkins with our next video. This one is about electromagnetic radiation or light. And so what we're going to do is we're going to start with a little physics. And when we're talking about energy, physicists talk about it in terms of fields, so particles moving in fields. So you have the strong field and the weak field. Let's get our pen here. These are both nuclear, so they're what hold protons and neutrons together in the nucleus itself. These are very strong, even though one of them says it's weak. Compared to the other fields, they're very strong. Gravity is another field. This is one we're well aware of. It's what keeps us on the ground, what keeps our planet rotating around the sun, etc. But in general, it's very weak, and we can ignore it. Except to say that we have to walk on the ground, and if we drop a beaker, it falls to the ground, so gravity affects those things. But the one field that's very important to chemistry is electromagnetic. So basically, all chemistry and chemical behavior falls in that electromagnetic field. Most everything else we can ignore. And you can imagine, right? So electrons are negatively charged, protons are positively charged. And so we have interactions between those two. That's what's holding the atoms together. And then later on, that's what's holding molecules together and so forth. So it's all electromagnetic, or in the electromagnetic field. And the way you transfer electromagnetic energy around from, say, one part of matter to another, or around the room, or move it around wherever it might be, is through light or electromagnetic radiation. Okay? And so what we're going to do is we're going to look at light, and light travels as waves. This is something that was observed many, many years ago. And basically it propagates as an oscillating electric and magnetic field. So if you want to think about it, you have an oscillating field. This is its direction of propagation. So this is the electric field, the electric vector. And then out here, kind of 90 degrees to that, is the magnetic vector. Okay, so you have the electric vector propagating in one direction, 90 degrees from that is the magnetic vector. And that's how light propagates. It propagates at pretty much a constant speed, which we call the speed of light. In this case, it's the speed of light, or at least to two significant digits, the speed of light in a vacuum. The speed of light does change depending on what medium it is going through, but pretty much it's pretty fast, right? So 3 times 10 to the 8, not minus 8. And so the properties of light depend on the wavelength. So what we have is these waves, and we're looking at the electric vector here. Sorry. And so we go from here, from peak to peak is the length of a wave. Okay, so that's our wavelength, which we use as lambda. Okay, if we were staring, here's our little eye, and we're staring at this point, the frequency is the number of waves passing. So you have the wavelength is the peak to peak distance. So this is a length. This is in meters or whatever it might be. And then frequency is in number of peaks you see, maybe in passing a point per second. Okay, so the units of frequency are seconds. The units of wavelength are meters. And because light is moving at a constant speed, frequency and wavelength are related to the speed of light, and so we end up with an equation where c is equal to lambda times nu. Okay, nu is our Greek symbol for frequency. Now we also show that light can act like a particle, because if you're thinking about waves, they're moving up and down, or it's an oscillating field, it doesn't really have any kind of mass, if you will, to push something, hit something like a particle. But it turns out there's an experiment, the photoelectric effect. This is basically if you shine light on a metal surface. Okay, we're going to represent it here, at a certain wavelength, and so a low enough wavelength. So if it's less than a particular wavelength, of the particular metal, electrons start coming out. So you could see electrons coming out from the surface. So you hit matter, a metal, with light, electrons are ejected. And as you lower the wavelength, the speed with which the electrons come out is faster. And this is particle-like behavior. This is not something that you would see based on the ocean. So the motion of waves in the ocean, for example. And they only come out below a certain threshold. If you make the wavelength long enough, then nothing comes out. It's just light shining on the surface. It does nothing. So there's an energy. So based on that, you can quantify the energy of light, and we're going to call it a photon. So sometimes people call this a packet of light. Basically, a photon is what you call light when it's acting like a particle, and it is also related to the frequency, which is also related to the wavelength. So the energy of a photon is equal to h times the frequency. Now h is Planck's constant, and it's 6.626 times 10 to the minus 34 joules is our unit of energy, so we'll get joules. The frequency is in 1 over seconds, so you would get joules for your units for this equation. You also see that energy can be related to wavelength. So we don't have to convert wavelength to frequency. We can just do hc over lambda and calculate the energy of a photon. And so what this gives us, so we have energies of photons related to the wavelength, so we can look at the electromagnetic spectrum. And here's one I took from online, which kind of basically shows, here's the visible spectrum, and I show that the wavelength of the visible spectrum is between 400 and 700 nanometers. So this is 10 to the minus 9th meters. So nanometers is 10 to the minus 9th meters. So they're pretty short wavelengths. So the shorter the wavelength, the higher the frequency, right? So we've shortened the wavelength, the more times it passes a particular point, because the speed is always constant, it's higher energy. Okay, so shorter wavelength, higher energy, longer wavelength, lower energy. And so just on the higher energy, shorter wavelength side of visible is the ultraviolet. You could go on to X-ray. On the lower energy, longer wavelength side, you have infrared, microwave, and radio, all of which at some point we'll talk about what they do, what we use them for. So let's go through this process and calculate the energy of a photon. So let's calculate the frequency and energy of a red photon, which has a wavelength of 625 nanometers. So if we go back, we're in the red, we're close to the infrared. Remember I said 400 to 700. 700 is really kind of a lot of people can't even see 700 nanometers. So we're getting closer to the red part of the spectrum. So 625 nanometers. So let's calculate the frequency. We know this is a wavelength. So frequency is, so C is equal to lambda nu. So I've just rearranged this equation. To solve for the frequency. We plug in the speed of light in a vacuum, 3 times 10 to the 8th meters per second. I've now converted wavelength to meters, so 625 times 10 to the minus 9th meters. If you're a stickler and you want this to be in scientific notation, that's the same as 6.25 times 10 to the minus 7th meters. But either way, it'll work out. And if you do the math, you get 4.8 times 10 to the 14 per second. Or actually the unit, that 1 over second, is the same thing as hertz. So anytime you see hertz, that's what it means. So this wavelength, and this is how fast light is moving, is passing a point 4.8 times 10 to the 14 times per second. So now let's calculate the energy. Now we have the frequency. We don't have to worry about it. We could have gone straight from wavelength to energy, but since we've got E equals h nu, our energy of our photon, we'll just plug in Planck's constant and this frequency that we calculated here, and we're left with 3.18 times 10 to the minus 19 joules. Okay, now to put in perspective, what is a joule in terms of energy? 1 joule is approximately 1 heartbeat. So every time your heart beats, you're using 1 joule of energy. So this 625 nanometer photon is 10 to the minus 19 heartbeats, so not very many of them. But remember, like we did in the last, when we're talking about formulas and molar mass, oftentimes we want to know macroscopic quantities. So let's figure out what the energy of a mole of photons. So we have a mole of molecules emitting photons, we would get a mole of photons. And let's see how much energy that is. So here we have 3.18. We just multiply by Avogadro's number, which if you recall is 6.02 times 10 to the 23rd, and it's 1/mole. We get, in terms of joules per mole, 191,000. I've shortened it to the 3 significant digits. These are non-zeros, but I cut it to, this is just based on sig fig. So if you do this calculation and you don't get exactly that number, that's why. And then I've simplified it from joules to kilojoules, so 191 kilojoules per mole of red 625 nanometer photons, and that's the energy. So here are the basic messages from this. So we've talked about light, electromagnetism, electromagnetic radiation. Basically, that's the field, that's the energy we need to deal with in chemistry. Everything else we can ignore. You may have known from physics, light can act like waves, light can act like particles. So we have the energy related to the wavelength. So there is where the two cross, right? So we have waves and particles, but they don't do them separately. They do them together. So here we have, wave and particle nature combined. So when we come back in the next video, we'll talk about how we use this idea of wave and particle nature combined. So until next time.